Okay, so my name is Brianna Hart, and I am doing my calculus project on evaluating integrals of rational expressions using long division and partial fraction decomposition. So I've written down a few things that I think are key concepts of this general material. The first thing that I have written here, for example, if you're looking at a problem such as, and we look at this and we say, okay, there's a 2 in the numerator and a 3 in the denominator. In that case, the highest power is actually in the denominator. So we'd be looking at this one. And when it comes down to the highest power in the denominator, we'd be using something called partial fraction decomposition. If the roles are reversed and we have a 3 in the numerator and a 2 in the denominator, then we'd have the highest power in the numerator here, and we'd be looking at this case, and we'd be using long division. So I think those are some important concepts to know the basis for this, because when you're looking at problems, you have to know where to start. I also have written down right here, we have just a example. This is the example. When you're looking at a problem such as one like this, you can tell that the denominator here can be factored. So this red piece right here is what I changed in it. I factored it to x minus 6 and x plus 1. We know how to do that, but the next part is something that's kind of newer, and that's just separating it into two different pieces, like this one and this one, so that we can take this piece and put it here, and take this piece and put it here. And the reason we do this is basically because if we're looking at something like this and we're taking the integral of it, we're taking the integral of this, we don't know how to do that. But when we break it down into pieces like this piece and this piece, we know how to do that. So I just wrote that I split them up here. So that's how you would decompose it. This next piece I think is interesting because it's a little bit different than what we're used to. So here you can see that it has a 3 as a exponent. You'd be thinking, okay, well, I'm just going to write it as x plus 2 to the third power. But as you can see, I highlighted here, here, and here in this purplish color. You have to actually write it out 3 times. This is like to the first power, to the second, and then to the third. This piece is a little bit different as well. You can see that it has a squared term in the denominator, and it cannot be factored any further than this. So that's why there is a d and an e in it, because we have dx plus e. Anytime that there's going to be like an x squared plus 4 plus 6, whatever number that there is, you're going to use like a dx plus e, because there's not a difference of squares here. It's a positive 16, so you can't factor it down. So technically you can even write this piece up in the front and use it as ax plus b and then do the rest as just c, d, and e. It doesn't matter the order, so this piece right here, it doesn't matter the order which you put it. And then I also wrote down here, this is like x cubed. It's like similar to this one. It's just not x plus 2. It's not like, it doesn't have anything after it. It's the same thing. And you can see here, I even put this one first. Like the other one I put last. This one I actually put first to show that the order doesn't matter. So here I wrote, x to the first, x to the second, and then there's x to the third over here. So those are just some of the key concepts. Moving on, I just want to show how you would do polynomial long division, because sometimes you do have to start with polynomial long division and then go into partial fraction decomposition. So let's say that we're looking at a problem like this. The numerator degree is greater than the denominator degree. And basically what that means is, okay, we can divide this. This piece right here, it goes into this piece a certain amount of time. So we're going to divide it before we even try partial fraction decomposition, because it will just make things easier on us. So here you can see that I set up the problem. I think one important thing that I want to kind of show is that I wrote a 0x squared here, There's not an x squared term in this problem, but you really want to have that 0x squared in there. So the next step is to look at the first term. As you can see, I highlighted the first terms here. The first term on this is an x squared, and then the first term in here is an x cubed. So all you have to do is you're going to look at this term and you're going to say, okay, how do I get x squared to look like x cubed? Multiply it by x. So that's where I put this x here, and you're going to want to put it above where it corresponds to. So you don't want it above the x squared, you want it above the x. So now once you find out that, okay, if I multiply this by x, I'm going to get an x cubed, you're going to continue that with each of these. So you're going to continue on by saying, okay, x squared times x is x cubed, x times x is x squared, and -2 times x is -2x. So that's where these numbers are coming in. And then you're going to put them in parentheses, and you're going to put a subtraction sign on the outside. So all the signs are going to flip on the inside. And then you're just going to subtract all those numbers, and you're going to bring down that 3 and continue on until you can't anymore. So after you do the same steps for this, you're going to get a solution where this cannot turn into this anymore, and this becomes the remainder. And what happens here, as you can see, I highlighted this and this, they correspond together, and these are actually going, that's where this is coming from. So x minus 1 is the solution, and then you're going to add the remainder divided by this piece right here, and that's where it's coming from. Why do we need to even use partial fraction decomposition? When you're doing derivatives, we have the quotient rule. So if we were taking like the derivative of, x squared plus x divided by x squared plus 1, we know, okay, we can do low d high plus high d low all over low times low. And that's how you solve the derivative. But there is no quotient rule for integrals, so we have to separate it into pieces that we know how to solve. So that's why we're doing something like that. And you can see, like, I wrote an example here. If we're looking at something like this, we need to separate it and break it down before we can even integrate it. Okay, so I just want to start off with some practice with partial fraction decomposition before we jump into anything with integrals. Okay, so all I did now was I just factored the denominator, which we already know how to do. Now we're going to start with the partial fraction decomposition. All you're going to do is turn that numerator into letters. So I'm going to start off with an a, and I'm going to divide it by this first term here that we have, the x, plus b divided by x plus 7, but remember we can't just square it, we have to create another one, plus c divided by x plus 7, and we can square this one. So we've taken care of the squareds here because there's 2 of them, and we've taken care of this x, and that is how simple it is. What you can see here in this problem, I took that x and I wrote it over a, or under a, and then for this piece, remember it cannot factor down anymore, and there's an x squared term in it, so that's where this bx plus c is coming from, and the dx plus e, and that's, to the first power and to the second power. That's how simple it is to decompose these, and now we can jump right into integrals. Alright, so let's take a look at our first problem. We have the integral of 2x cubed minus 12x squared minus 31x plus 7 divided by x squared minus 6x minus 16. So the first step is to look at the degree of the numerator and the degree of the denominator. And we can see here that the numerator degree is greater than the denominator degree. So we're going to first have to go through with long division. So I'm going to do that really quickly. So I have written out my little fraction here. So we're going to need to multiply x squared by 2x, which will go right above this negative 31x. And we're going to start multiplying each of these terms by that 2x. Alright, now we can start subtracting. Okay, so here's our solution to the long division. We are going to now continue on with this problem. So we know that these are equivalent which means that if we take the integral of 2x plus x plus 7 divided by x squared minus 6x minus 16, we'd get the solution. But we still are not done, because if we look here, we have a piece where we can use partial fraction decomposition. So let's work on that. And what I'm going to do is I'm just going to highlight this piece so we know we have to come back to it. Right now, we're going to strictly work on x plus 7 divided by x squared minus 6x minus 16. Let's decompose. Okay, so now we have our piece here, so now we can solve for a and b, and to solve for a and b, I'm just going to multiply by a common denominator, which would be x plus 2, x minus 8. And when you do that, when we multiply by x plus 2, x minus 8, what's going to happen is this piece right here is going to be left as just x plus 7, because they're going to cancel in the numerator and denominator. This piece is going to be a times x plus 2, and this piece is going to be b times x minus 8. And to solve for a and b, we can pick numbers that we know will simplify out to 0 for a and b. So let's choose x equals -2 and x equals positive 8. -2 plus 7 is 5. -2 plus 2 is 0, so this is going to be 0. -2 minus 8 is -10. Now we can rewrite this as 5 equals -10b. Divide by -10. We're going to have -1/2 equals b. Alright, and here I'm just doing the same thing to solve for a. Have solutions for a and b, but we're not quite done yet. Remember, we still have this piece up here that we have to integrate, and we still have to plug these pieces back in for a and b. Okay, so x plus 7 divided by x minus 8, x plus 2, and we're taking the integral of this, and that's going to equal of 3 divided by 2 times x minus 8 plus the integral of b, or -1 divided by 2x plus 2. We're going to start with this integral right here. The first thing that I notice is that we can pull that 3/2 out of that integral, and we'll be left with 1 divided by x minus 8. And we can pull that -1/2 out of this one right here. So I'm going to have -1/2 times the integral of 1 divided by x plus 2. Now you can do u substitution here. I'm just going to go ahead and go in with the natural log. I'm just going to solve this as 3/2 the natural log of x minus 8 minus 1/2 the natural log of x plus 2 plus c. But we're not done, because that's not the full solution yet. We have to remember that there's still an integral over here. We have now solved for this piece, but we still have to do this piece. So let's just take the integral of 2x over here. So the integral of 2x is just going to be 2x squared divided by 2, which is simply x squared. So let's add that into our solution. And you only need one constant c. We don't need to add a c for everyone. You only need one. And this is going to be our final solution here. Alright, so now we're going to do more of a complicated problem. In this one we don't have to do long division because the denominator's degree is greater than the numerator's. Alright, so I've put this into the partial fraction decomposition form. Now we're going to need to solve for a, b, and c. And this one is a little bit different because if you see and you notice here, this is a bx from plus c, whereas what we solved in the last problem, we only had single variables like a. Is we're going to actually have to multiply this by a common denominator, and that is our common denominator here. When we multiply out with that common denominator, it's going to simplify to... Alright, so now that we multiplied out with that common denominator, we're going to need to pick x's that we know will cancel out. Put a positive 1 in for x and we multiply by 0, this whole piece right here is going to simplify out to 0. So let's pick x equals 1. Okay, so we know that a equals positive 1, and now I'm going to plug in 0 and try to solve for b and c. The reason I chose to put 0 in is because right here, b times 0 is going to be 0, and we already know what a is, so we can plug a back in. So I want to get c and a alone. Now that we know that a is equal to 1, we can plug that in. So we solve for c. Now we can pick another number where we can plug in, and we know a and c, so it shouldn't be a problem which number we pick. I'm just going to pick a -1 because I think it won't be too difficult. Here, all I'm doing is anywhere that there is an a or a c, I'm plugging in either 1 or -1 based on what letter it is. And then I am plugging in -1 for x, so those are where all those different ones are coming from. And now we know a, b, and c. Now we're going to take our a, b, and c terms and plug it into this equation that we have down here. I just copied and pasted it from the beginning. Okay, so all I'm doing here is I'm just plugging those a, b, and c terms in from that equation that I have there that I just copied and pasted from earlier in the video. Okay, and all I'm doing here is separating that very last integral into two separate integrals with the numerator -x and -1. Alright, so for this first term right here, we know that this is just the natural log of x minus 1. For this second term here, we can use substitution. So the solution to this is just going to be -1/2 the natural log of x squared plus 25. One is a little bit more tricky. There is no substitution for this one, but if you notice, this looks similar to our tangent, inverse tangent function. I'm going to pull out a 25 in the bottom. All I'm doing now is I chose my u to be x over 5, found the derivative of that, and now I'm getting it to look like the inverse tangent function so that I can integrate. Alright, so now all those green little solutions down there, those are all of our answers that we must combine together. So all those that I just highlighted. Alright, and now I'm just going to combine all of our solutions together, starting with this one, then this one, and then this one. Alright, so I combined our solutions together. Okay, so as you can see, I'm going to start highlighting where I got those from. And that is how you find the solution of this last problem. Thank you for watching.